So welcome. In this video we are doing a numerical or static timing analysis. So we are given that the clock to Q delay for the launch flip-flop is 5 nanoseconds. It means it will take a time of 5 nanoseconds to produce a data at its output. Then we are given that the delay of the combinational logic is 2 nanoseconds. So the data will take a time of 2 nanoseconds to travel through this combinational logic. Then we are given that hold time is 3 nanosecond and clock skew is 6 nanosecond. So what this clock skew means? It means if the clock at launch clocks arrives at t equal to 0 nanosecond, then the same clock pulse will arrive the capture clock at t equal to 6 nanosecond. So it means there is a clock skew, because here if the clock signal arrives to this launch flip flop at 0 nanosecond, it will arrive at this capture flip flop at 6 nanosecond. So in this numerical we have to find whether there is hold time violation or not. So we are drawing the waveform at launch flip flop and capture flip flop. So let's suppose that the clock pulse arrives to the launch flip flop at t equal to 0 nanosecond. So it will arrive to the capture flip flop at t equal to 6 nanosecond, because there is a clock skew. Then we are given that the hold time th is equal to 3 nanosecond. So it means that after the arrival of the clock pulse, the data must be stable for at least 3 nanoseconds for it to be correctly latched by this capture flip flop, or for correctly capturing by this capture flip flop. So it means that the data should be stable in this range. So from 6 nanosecond we can add the hold time of 3 nanosecond. So it means that the data arrival time or the data required time is 9 nanosecond. Because when we are capturing this data, suppose we are capturing the data D2, then for at least 9 nanoseconds this data D1 should not arrive. Let's suppose this capture flip flop is capturing data D2 and the launch flip flop is having data D1 at its input. Then the data required time is 9 nanoseconds. So it means that when this capture flip flop is capturing this data D2, then for at least 9 nanoseconds this data should not arrive, otherwise this data will not be captured perfectly by this capture flip flop. So the data required time is 9 nanoseconds. Hence the new data D1 must arrive to the capture flip flop only after 9 nanoseconds. So we can say that the data required time is 9 nanoseconds. Now we will check for the data arrival time. So again we consider that the clock signal arrived to the launch flip flop at t equal to 0 nanosecond. So it arrived here at t equal to 0. Now this clock to Q delay is 5 nanosecond. So it means this data D1 will be available at the output at t equal to 5 nanosecond. So it means that at 5 nanosecond it is available at this point. Then this combinational logic delay is 2 nanosecond. So somewhere here at 7 nanosecond this data D1 will appear here. So again, but we consider that the data required time was 9 nanosecond, but here the data arrival time is equal to 7 nanosecond. So it means that there is a hold violation, because we have this new data D1 appearing at the input of the capture flip flop when it was capturing this data D2. So it means that there is a hold violation. There is a hold violation in this circuit. There is a hold violation in this circuit. So how we can reduce the hold violation? we can either is we can either slow down the data path. We can slow down the data path. Suppose if I increase this tcomp from 2 nanosecond to 5 nanosecond, I have changed it from 2 nanosecond to 5 nanosecond because we were having a hold violation here. This new data D1 was corrupting our data D2. So now we will take it with this combinational logic. Delay we have increased to 5 nanoseconds, which means we have increased the data path delay. So what we can do is now the data TC2Q does not change, so the data is arriving here at 5 nanosecond here only. But tcomp is now again 5 nanosecond. So this D1 it will take 5 nanosecond. So now it will arrive here at 10 nanosecond. So now this point is changed to 10 nanosecond because it was 5 nanosecond. It was appearing at this point at 5 nanosecond. Then combinational logic delay is 5 nanosecond. So now it is appearing here at 10 nanosecond. So obviously 10 nanosecond is after 5 nanosecond. So now there is no hold violation. Now there is no hold violation. So what we did was we removed the hold violation by increasing the data path time. Or what we can do is, this was the first way. What can be the second way? We can reduce the hold time. So suppose if we make the hold time to 1 nanosecond, so it means that this t becomes equal to 7 nanosecond. So if this is 7 nanosecond, again 7 nanosecond, so there will be some violation. It may be, so we can reduce the clock skew also to 5 nanosecond. So it means that here it is 5 nanosecond and 1 nanosecond, so this is 6 nanosecond now. So 6 nanosecond and 7 nanosecond, so there is no hold violation. So for the hold violation, the data arrival time must be greater than the data required time for no hold violation. So here we reduce the data required time to 6 nanosecond and data arrival time was 7 nanosecond. So there was no hold violation. Or if the data required time is 9 nanosecond, then as we discussed earlier, we increase the data arrival time to 10 nanosecond. So what we can do is, we can either reduce the data path delay or we can increase or we can reduce the clock delay. So in this way we can remove the hold violation. Thank you.